Okay, so now we're going to take notes today on atmospheric conditions and the atmosphere. You'll definitely want to go through this slide because I'm going to go pretty quickly through it, but you'll want to go through it on your own. I'm going to point out some key features as well as what you guys are going to see in the practice. So the Earth's atmosphere is consistent of nitrogen and oxygen. You guys probably already know this. The atmosphere is how we sustain life on Earth, and it protects us from solar radiation. Those are all things that I think are just known in the general population. The next thing that we're going to talk about is when we talk about flight, we can't get away from atmospheric conditions. And moving forward, especially when we talk about space, when we get into the space aspect, we're going to be talking about these atmospheric conditions. So there's a thin sheet of air that's about 60 miles thick that wraps around the Earth, and we're going to kind of talk about that 60 miles thick and what that looks like of air and the different layers. So that's where we start, is with the different layers of the Earth's atmosphere in those 60 miles. So in those 60 miles, let me see if I can zoom in here. I think I can if I am careful. Whoops. If I'm careful not to put my cursor on here. Okay, so here are the different layers as well as the dimensions, like where those are. And as you get higher, as you guys know, air density gets less, the pressure gets less, to the point where when you're in space, you have no pressure or gravity. So that is what you're kind of seeing here, this cycle in and out. But this, the closest one to us, the closest ring to us, is known as the troposphere, and that's within the tropopause. Now, that takes us to 36,000 feet. Our flight happens at below that. So like when we're flying planes, that happens below that. When we're going into space, obviously we go through that, but into the stratosphere and beyond. But that is the idea of flight. Flight happens below that value in the tropopause. So even Mount Everest is at 29-ish thousand feet. I don't remember the exact. That's the highest place on Earth, and it still happens well within the tropopause. So that's something to take note of. Beyond that, 36,000 feet, we have the stratosphere, followed by the mesosphere, followed by the thermosphere. So those are the different layers of air that we're talking about in that 60 miles from Earth before you get into space, and the layers. Okay, so that's the first part, is just knowing that. Also knowing that air pressure is changing within those different air pockets. So the density and pressure are higher the closer to the ground that you are. So gravity plays a denser and more pressure to us. And that's why when you start to drive into the mountains, your ears start popping because that pressure is coming off of you. So it's that concept. Okay, and again, that's probably something you guys already know a little bit about because we deal with that on a daily basis. So here are the calculation parts of what we're going to be looking at moving forward. So aerospace engineers use a standard compare measurement such as speed in order to go through the next calculations that we're going to use. So 15 degrees Celsius and 101.3 kilopascals, 59 degrees Fahrenheit and 14.7 PSI. These are kind of like standard comparisons that we're going to use, okay? So I'm going to move on to what that means. Okay, so when you guys look here, the Earth's atmospheric conditions, when we look at the first it's like sea level, then we have 4,000 feet above sea level, we have that 8,000 feet, then the 10,000 feet. We have some standard calculations that we're going to use, and also we're related. These right here are locations or degrees in Celsius. We're going to look at those in our measurements in the next one. So this is like a standard grid of where they are getting some of the calculations in order to talk about lapse rate in the troposphere. Troposphere is, again, that sphere, the closest one to us before you get into the stratosphere. So these are the calculations that you just saw, that 15.04 Celsius. That is used when we're talking about temperature. When we're talking about temperature, the way that we are going to calculate in regards to where we are in the troposphere, we have that temperature, and then we minus a constant where we have our degrees Celsius over the meters, or the height in meters, times that height. So Celsius degrees per meter, and then this is the calculation for pressure. These formulas are given to you guys on your formula sheet. That's the one thing I haven't supplied you yet with that I need to actually, I'm going to upload that because we will be using this for our problem set tomorrow when we practice. We're going to be using this. They're going to ask you for the pressure, and they're going to give you certain aspects in here, and you're going to go through and solve. So that's going to be the idea behind these atmospheric conditions. And I'm going to show you some of that. This right here is air density. So if we are looking at an air density, it is very difficult to tell the difference between these two. There are basically three different formulas that we'll be using tomorrow. We'll be using the temperature one. If they're talking about temperature at a certain height, the way that you're going to get that temperature is going to be to plug in the height. Or if they give you the temperature and they want to figure out the height, then you can use this formula. The other one is this one right here, which is pressure. This is pressure. I'm going to pop over to this one so you can see it is a very subtle difference. This P, that's pressure in the last one that we were looking at. This little P right here with no little curly on the top is known as density. Most of what you guys are going to calculate is the density. In order to get the density, you're going to need your air pressure. So in the problems, when we look at it, you'll need to sometimes go through and calculate pressure based on temperature that you're given. And then from there, once you have that pressure, you plug it into this formula in order to figure out the air density. The air density. So air density in our problems will typically be the end result. But in order to get there, we'll need to know the temperature and the pressure. And this is for calculating Earth's atmospheric conditions. Okay, this goes on to tell you a couple more things. This is just kind of interesting in my mind. Mount Everest is 29,000 feet in the air. Climbers have to acclimate over like long periods of time. If you guys have ever seen any of the movies for Everest, it's super interesting. There's definitely a high death rate on climbing that mountain, and it has to do with that the pressure aspect and the atmospheric conditions. It always is snowy up there, and there's definitely atmospheric conditions which are different there than, let's say, San Diego. So that's, again, something that there's loss of pressure. People get altitude sickness, obviously, and there's very low oxygen levels up there. Okay, so the last thing that you guys have in here is talking about the aircraft speed and speed of aircraft. Your practice won't have any of this in it, but on your quiz, I'll definitely kind of talk through, or I'll have problems from this as well. But aircraft speed, as you guys know, this is a sound barrier that this plane is breaking here. That's probably something you've heard of or experienced. Maybe you've been to see a Blue Angels show, although they just waver at the sound barrier. They won't actually break it at air shows because it causes what's called a sonic boom. So this right here goes through and tells you the air speeds and where the air molecules transition between beyond the speed of sound. Obviously, the higher up you are, these are going to vary a little bit, but Mach speed, when we talk about Mach speed, subsonic speeds have a which would be any kind of commercial airplane, they have a speed less than Mach 1, which means that you're looking at traveling less than 761 miles per hour if it was at ground level. Again, the higher up you get, this changes and varies. That's what the pressure has to do, and the density that you guys, air density that you guys will be calculating later. Subsonic is going to be from Mach 1, which would be, so like Mach 1 to Mach 5 is above 761 miles per hour. And then we have what's called hypersonic speed, which is Mach 5 to Mach 10, and high hypersonic, which is Mach 10 to 25. So we'll talk about aircrafts later on with this. I will say that the higher you are in higher altitudes, the slower this speed is, meaning like it will take less time to achieve that Mach 2, Mach 3 speed, the higher that you are. So Mach threshold is lower, meaning these values will be a lot lower. Okay, I'm going to stop there. Go ahead and take notes on what I just said along with the PowerPoint, and we'll check in for calculations tomorrow.